So today I thought we'd return to the input switching circuit that we looked at in the previous video, just to sort of see what we learnt from having built one, what we might do differently next time, and where we're heading with the rest of this project. But first, I think we'd better get this out of the way. I am such a child. So the first thing I got horribly wrong was that I used the footprint of the wrong relay. So what I had with these Panasonics, which have the same footprint as a Omron G6S, and when I was laying out the board, didn't pay attention, just looked at the sort of basics of the that we have a group of 6 and a gap and a group of 2. All looked sort of similar. It was Omron G6, though it's G6Y, I believe, is actually the pattern. So I had a bunch of these and a board that they don't fit into. So thankfully, one of the suppliers had some of these, so we got the correct relays and could move forward. So the next thing I got horribly wrong was to choose a connector for my ribbon cable without paying any attention to the cost of the crimping tool. So these are Molex Pikaflex connectors. It's an 8-pin one. Lovely little thing, relatively inexpensive. Lots of nice things to say about that, except that the crimping tool required for these costs over 2,000 Australian dollars. And with the greatest respect, that's not going to be happening for a hobbyist. Fully understand that in a production environment, where you need a reliable connection, and you've got an operator who might be using one all day long, that's probably entirely justifiable for them. But for a hobbyist, no. So I tried to get by sacrificing one of these PCB headers by taking the PCB pins off the bottom, making that flat, and then hopefully having something that I could crimp in a regular IDC crimping tool. Had a lot of trouble with that even, because that would catch the edges of this, and I destroyed a few of those. I've had various goes at it. I've still got a few left, but I still haven't managed to make a reliable connection. Eventually I just resorted to buying pre-made cables, which thankfully are relatively inexpensive. So that got me out of trouble. But I am questioning whether to continue with that style of connector in the future. It's perhaps not a hobbyist friendly item, although these do the job, and that would be okay at a pinch. Not only that, I made a couple of little errors in laying out this little daughter board for the LEDs and the switch. The first notable one is where I position the switch, where I should have had that up level with the edge of the board, and for some reason I've set it all the way back there, which doesn't make a lot of sense. And the other thing too is I've just put the diodes 1, 2, 3, 4. I've just laid them left to right as I was looking at the board, as I was designing it, without really thinking about how it would look facing towards you. That's okay, because you can just flip it over and put it upside down, and that sort of works, so that'll do for the moment. But that's not too bad. So the next issue is an interesting one. So one of the things that I didn't pay attention to, and I can't believe I missed this, was how the unit powers up. I didn't take sufficient precautions to make sure that the 4017 would be reset at power up. And that leads to a situation where sometimes it'll power up with the first input enabled, or the second, or it'll step through if you only turn it off for a little while. Thankfully, I've never seen it come up with the 4017 with one of the unused outputs enabled, in which case you'd have to keep stabbing at the button until you got round to one that was actually in use again. So it's not too bad. It's probably acceptable as it is, but naturally I had to come up with a solution. Okay, so here's the part of the circuit in question, and in the previous circuit we simply had this connecting round here from the output into the reset, and that was it. Which is fine as far as getting it to step to number 4 and then back to number 1, but it doesn't deal with our startup. So to deal with the startup situation, what I've gone with is a 100 nanofarad, that doesn't right, there we go, cap here, and a 100k resistor to ground. So if all we wanted to do was to bring the reset line high briefly at power up, that would be all we'd need. But because we're also using the reset line to deal with only wanting to count up to 4 and having it reset on the 5th output, then we're going to need these 2 diodes, because we don't want these 2 different things that pull the reset high to interfere with each other. So for instance, we don't want this cap here to get discharged when this operates, so we want this to get charged up once when the 5-volt rail is energized, and to stay that way until the power goes off. So I have reworked the circuit, I've respun the board. As to whether I'll build any of those at this stage, I'm not sure. I'm happy to go ahead with this one as it is. It generally powers up with the first input enabled. That's not ideal either, of course. If it had some sort of memory, that would have been a better user interface, but it'll do. So as you saw, I decided to go ahead with the LED board for the input selector, and I've kind of abandoned the idea of using a Nixie for that specific application, mostly because inputs aren't really numbered. I mean, numbered 1 through 4, it's kind of a bit silly. I mean, it'd be nicer if they were named really rather than numbered, so it didn't make a lot of sense. But I've got something else in mind. So to wit, here's a little design I've come up with for a BCD driven Nixie display. So we're using a 4028 CMOS BCD to decimal decoder. These are 10k resistors here, and these are all MPSA 42 high voltage transistors. That's basically how that works. That just switches the cathodes. That's all good, fairly simple stuff. However, I sort of thought it'd be nice to have a logic input that would enable the output so that we could do blanking. You can actually do blanking by putting an illegal number into the inputs there, and the decoder will not energize any of the outputs. That's one of the ways to do it, but I don't know, I had this thought, you know, you could do PWM. I'm not sure I want to do PWM inside of any box that I'm wanting to use for audio purposes, just from a noise point of view, but it's nice to have the option. So I thought, okay, we need to switch the high side. So we've got a high voltage supply at normally about 170 odd volts. How are we going to switch that with a logic level input? So what I've gone with is it's an MPSA 92 PNP high voltage transistor, and that's the top of my head. We have, I think it's about 10k. This is not writing well, is it? That's not writing well at all. Here we go, 10k there. These are about 100, I think. 100k there, and 10k there. So this is an MPSA 42, just like these. So basically what we're doing is we're doing low side switching here, where the voltage that appears on the base of this transistor is going to be safe and perfectly okay, in order to switch this transistor here. The reason why we can't just switch that directly, of course, is that that will be a diode drop away from our 170 volts, and that's not going to end well. So why have I come up with this circuit? What am I intending to do with a BCD driven Nixie. On to the next bit. Having had so much fun with the relay switching for the input selector, I went all out with my attenuator circuit. So this is a fairly typical stepped attenuator circuit. It's basically a sequence of L pads. It's all in those resistor values, but if you get it just right, then you do actually get a logarithmic attenuator, and basically by applying a binary number to the input here, you get a specific amount of attenuation on the output. In this case, I was trying to find an economical solution using E24 series resistors, and I also came up with one using E96 resistors, which was super precise. And you can pretty much guess which one I've gone with. I've gone with the crazy version, obviously. So my choice here was to go with, it's actually 6 bits, because this one here is actually just a muting circuit, because we've got no resistor there at all. So it's 6 bits, it's 64 steps, and each of those is about 0.85 dB with the resistors that I've picked. Now I've put buffering on both the input and output sides here. We need buffering on the output side because the output impedance of this is all over the place, although the input impedance is fairly constant at about 10k ohms. But I'm kind of liking the idea of buffering at both ends. Still not completely sure on that, but I'm going to go ahead with that. So that gives us about 56 and the change dB of attenuation, a maximum, and that's the reason why I've added the 7th relay for a mute. So that makes no sense, of course, to use in combination with all the others. It doesn't do anything. It's not like a 7th bit. It's really a 6-bit attenuator with an added mute. Now, here's my thing. I want to use the Nixie display to display my volume level. I thought that'd be pretty cool. You know, you turn the volume knob, there's the clitter-clatter of relays, and the volume level you've selected appears on a pair of Nixies. I think that's suitably retro-tastic. But because one's BCD and the other is binary, I could try and come up with a way to do the conversion using logic chips, but to be honest, it's getting a bit out of hand. You might want to use an encoder for your input, so it's looking like I'm going to have to use a microcontroller. I don't think I can avoid it. So there you go. My desire to fool around with Nixies has dragged me kicking and screaming into the 1990s. Anyway, that's where things are at for the moment. Hope you've enjoyed this, and as always, thanks for watching.